Good afternoon, everyone. Welcome to this joint seminar between the QSC and the Elmore Center here at Purdue University. My name is Blake Wilson. I'm a PhD student here in CE, joined by my advisors, Vlad and Sasha. And today we have Professor Sorger here. Professor Volker Sorger is an associate professor in the Department of Electrical and Computer Engineering and the director of the Devices and Intelligent Systems Laboratory at George Washington University. Volker will give a short 30-minute lecture covering the material presented below. And I'll get into that in a second. And then afterward, we'll engage in a fireside chat between he and myself to discuss emerging frontiers at the cross-section of machine learning, quantum computing, and photonics. So today's talk from Volker will be about the fundamentals, from fundamentals to applications, a forward look for AI, ML, and quantum systems.
All right, thank you very much. It's really like a pleasure being here. I think for the camera, maybe I stay put here for right now. But oh no, we have this camera as well. Wonderful, so I can even move around. So welcome everybody to this sort of a presentation here, to this talk, and looking forward to to the fireside chat as well. First of all, congratulations to a fantastic new institute. I think these are very timely topics. Of course, the students and myself and others are very excited about. So, congratulations, Professor Bolter-Sever, for this leading this excellent direction. And I think if I got the background of the center correctly, I think there's a thanks bill in order. So yes, I got it right. Excellent, good. Pass. Woo. This is again this overview we briefly looked in already recently about my lab. We look into machine learning systems, some devices, some quantum matter, some technologies on the quantum side that we're working towards to now, and also work in cryptography for a whole bunch of basically nice applications. Unlike maybe a seminar, this seminar is a little bit forward-looking. So it's maybe less so just presenting what we have been doing. It's a little bit of a combination of here's something we have been doing, and here's something where could we go into in the next? What might be their projects and directions that might also interest you, you as a graduate student or even undergraduate student, that we can basically work together. Of course, the context of this is information processing and AI, ML, and then these quantum information processors and a bit of applications. So I thought to offer a bit of we talk a lot about energy, about devices, systems, computing. And a couple of years ago, we asked ourselves, so is attojoule per bit, 1 attojoule per bit, a fundamental limit or not? And in this entire compute context. So, and the way we looked at that is, this is a device level view. And you can basically look at it from saying, okay, so you have so many energy per bit that you, let's say, burn. That directly corresponds to the numbers of photons per bit. And this is, in this classical regime, this is basically where we are right now. This is state of the art. Good, okay. Meaning we're basically burning on the order of tens to hundreds of femtojoule per bit, which means for every bit we send over a certain distance over, let's say, a fiber optic cable, we're basically using 100,000 photons for every bit. Now, can we reduce this? And the answer is probably yes. Now, if we look at the x-axis and the top x-axis, essentially if you apply a device capacitive-based model on resistance and capacitance, you can basically pretty much convince yourself that a very short length essentially allows you to have a relatively high speed, because the lump capacitance basically drops, provided you have a reasonably low resistance, which could be challenging for very short, very small devices, which is based into this kind of model, very right here. In the third axis, you see actually power burn. So if you simply multiply the y-axis with the x-axis, you see joules per bit, bits per second, bits cancel, so joules per second is basically watt. This is the amount of dissipated power per unit device. And if we are in this classical world right now, where we drive devices on the order of tens of gigabits per second, we're burning hundreds of femtojoule per bit. You're basically burning 1 milliwatt per device, which means this current laptop I'm driving this presentation from has about 30 watt of power dissipation. So you can essentially think about 10 to the 4 devices on a, let's say, chip, which would consume the entire power of this laptop. So 10 to the 4, if you remember from electronics, it's not a very high scaling, right? It's kind of maybe 1970s. So the question is, can we kind of go beyond this? And of course, the entire field of nano-optics and nanophotonics, for example, lives in this field where, and here it comes now, this arrow I'm showing next is steeper than these iso power curves. So yes, if you would be down here in the sub-femtojoule, meaning in the hundreds of attojoule regime, at let's say again this 10 gig speed, yes, then you would actually burn a microwatt of power. Notice this error, we need this paradigm shift. We need to be steeper than these iso power curves. Yeah? How can we do that? Well, the idea in the like it's in the nano-optics field is essentially that you address this Q over V. This is the basic cavity factor or Q factor of a cavity, the quality of a cavity, divided by its own mode volume size. So if we now starting to basically crank up on this sort of concentration factor, you can actually design optoelectronic devices which are improved in terms of like power, both power dissipation, speed, and also basically, yeah, joule per second. Now, of course, the ultimate limit would really go to essentially this one here, right? 1 photon per bit, which would basically get us into the regimes where this Q over V factor had to be very, very high, significantly, 10 to like 10 to the 3 and or higher, which is something that can be done. In fact, there's some, yep, we have some examples basically here as well. Yep, and I think it's an interesting guideline for us. So now this doesn't answer the question, well, is 1 attojoule a fundamental limit for, let's say, device switching, and certainly about like signal processing. There are two ways to look at this. One look is to simply say, look at capacitance model. Let's say you have the smallest, think about the smallest material you can think of, and then the smallest charge. The smallest charge obviously is single electron, right? So you take the smallest piece of material you can think of, here are a few examples, and you add 1 charge to it, there you go. And then you have some capacitance change, some delta capacitance. That's the absolute fundamental smallest sort of delta C capacitance you can have. And let's just say, we are in optics and photonics, let's say this electron was absorbed by a photon of 0.8 eV, which is a typical telecom wavelength. You basically end up with a very simple number here of basically a fraction of an attofarad. So let's say this drives a capacitor of basically, let's say using 1 volt, which means you have 0.2 attojoule per bit. Very simple. So 1 attojoule is not the limit, but a fraction of an attojoule is the limit. The second picture is very simply, well, what if that photon is just 1 photon? And the energy of 1 photon, of course, is long and behold C over lambda, and if that happens to be again 0.8 eV, it is basically 1.1 attojoule per bit. So a fraction of an attojoule is the absolute fundamental limit we can probably ever get to. Interconnect people, right? DARPA, Dodo's program, and so on. Basically, we're talking about picojoule per bit. So there's still a long range to go. If you build an interconnect, it turns out the minimal interconnect noise is, of course, given by Shannon's noisy channel limit. Depends on the bit rate, and depends, of course, how noisy your channel is roughly in the order of tens of attojoule per bit at room temperature. Of course, if you drop temperature, then everything gets better as well. Here is sort of the other Moore's law. So device people, right? So you have basically, this is our plot from Intel. These are gates. If you have your gates, you scale. This is time. You scale. Here's the critical dimension. You get to this tens of nanometer short or 7 nanometer devices. Then you can plot the again the energy per bit, either in kBt, or here just also overlaid with in joules. In this case, let's say this is for zeptojoule. This is for attojoule or for femtojoule. So a single device basically is already on the order of tens of attojoule. That's great. But if you connect it now, if you add the simple capacitor to it, which is just a few microns short on a modern transistor, you're already up to the gates. You basically are already losing a factor of basically 100. That's why David Miller, for instance, always says, we need to package devices very tightly, basically photodetectors very tightly with transistors, for example. Now, we can overlay this now with photonic devices. So here are a few devices from my own group where we basically looked into these modulators, for example, and here's some works like over the years, and here's some that we're still working on currently right now. This is an archive where we basically see, in terms of energy per bit, we can really push this down to right now, even without a cavity. So these are all without cavities into the basically tens, let's say hundreds of attojoule per bit. If you add now a cavity, so any energy per bit can be improved by the finesse of the cavity, which of course relates to the Q factor. Then you can even push it down into the again, few to tens of attojoule regime. So it's kind of very like an exciting curve here. Again, this is the absolute limit without cooling. Once you would cool, you can go down. But there is a technology gap, certainly, that will be fundamentally very hard to bridge because you always have like the noisy Shannon theorem, which really eliminates from you to going like even further. Might be some opportunities maybe in with more cooled systems down the road. What's great about photonics, however, is we have this WDM, like this parallelization option. Yeah, we can drive multiple channels now across this. So even so, it looks basically photonics or optoelectronics and electronics are pretty much the same on the device level. What about the link level or system level when we talk about machine learning, accelerators where we need to send signals to different nodes? Turns out actually at that level now we are on the device level, we're similar, but we can harness, of course, WDM. That's one thing, this part. Second part is we can drive the baud rate at a single device level much higher than, of course, an electronic circuit because there's no capacitive loading, right, of a circuit. That's actually kind of interesting and certainly exciting. So for 6G, again, we need to be more than 100G, so that's a good roadmap. I dug out this old paper from 2003, incidentally, like a little fun fact, where these gentlemen basically were exploring, like using Heisenberg basically, what's the fundamental limit of any technology ever, right? And this electronics transistors. Okay, so we see a speed here of, let's see, 75. So they were forecasting here 21 years ago, they were forecasting in 2020, we will have, what is it here, like 12 nanometer node with 6 nanometer gate length and at 73 gigahertz. This came true, we all know that, we're right now at 7 nanometer, but this came not true, and of course we know why, right? It's because of the IC delay. Nothing new basically here, but just interesting, someone to look back 20 years. So, advice maybe for students, if you see a paper, that you read at some, like at some point, you can go back and forward and sort of like see how thoughts have shifted or came true or not true. And I think there's good things to learn. Okay, so that's the first point. Second point, you really want to be very synergistic in terms of how we design devices. Synergistic means there are certain sometimes parasitic effects, things we don't want, but can we be creative and think about that we still use these parts actually for a good cause. So this is something that I'm sure a lot of you already know. This is the Drudo model, in this case for indium tinoxide. So you can change, so with the frequency, the real part, imaginary part, permittivity, and optical index. If you change the carrier concentration, as shown these colors here, which is basically here changing like the plasma dispersion term, you can basically really dramatically, let me highlight this here, you can dramatically change the index for phase shifting based devices. But guess what? Kramers-Kronig gives you also like a delta kappa. Yeah? Now these are coupled. You may like delta kappa, like in this device here, or you may not like delta kappa. This was an old device. It's literally capacitor. You apply voltage. They sync up. They move. You change this carrier concentration right here, and you move from here to here. And long and behold, you can have some absorption, and you can have a device. Now, if you look at this plot down here, actually, this is the carrier concentration. Versus, if I go one, actually it's overlaid already. This is dn over d kappa. This is, in other words, if you're in this shaded region, you are n dominant. You can basically make phase shifters based materials or devices. When you're in this regime on the right here, you're actually kappa dominant. You can make absorption devices. So you can really tune this now where you want to sit in terms of like your device performance. This particular device was an electroabsorption modulator, which is basically at this epsilon near 0 interesting point where you see like epsilon here is basically 0, you flatten the mode and so on. There's some interesting effects happening. But you basically get both effects, like delta n and delta kappa. So can we use both synergistically? And this is something we did here. So if you think, let's say in modulator, for example, an electroabsorption modulator. So the idea is you send light in, you have a little control element, you want to basically kill the light, like here, less out. What you can do now is you can actually use, in this linear device, delta n is basically wasted. Can we use this? Well, we can. We obviously built a little switching node. You just couple, there's a two-mode coupling, that's symmetric and antisymmetric coupling. And then they couple over, and some of the light is basically so deflected, if you so will. So the downstream light is being reduced even further than just absorbed. While if you don't apply a voltage, this particular material here, actually it's just in dielectric. You see the index here, it's about 2, it's hardly any loss. So this is nice because if you look at now the voltage characteristic of such a device, it's pretty steep, it's very efficient. You can switch this with less than 1 volt. It's prospectively broadband, there's no cavity. So this is like, I call it generation 1 device, and you see this like deposition, all this like nanofab processing. So yes, this uses the nanofab extensively, like this kind of work. Generation 2, I mentioned briefly yesterday, is a directional coupler-based device that we now optimize for speed. So this is the, I think, yes, to the best of my knowledge, the fastest ITO-based modulator to date. It's like about 25 gig. We are still improving this further up to, in fact, this device of 50 gig, and we have another device I mentioned yesterday. We're pushing to 100 gig right now. Again, what's interesting, if you again look at the voltage swing, it is really efficient. It's just a fraction of a volt. This, of course, shows in the energy per bit. So again, I'm just showing these devices again as a sort of synergistic engineering concept that we can think about. So again, maybe advice for students, right? So if something is bad, it doesn't have to be bad. You can maybe use it also for something positive. So some devices for this neuromorphic computing. So yesterday we talked a lot about these vector matrix multipliers and tensor core processors. There's this entire other field about where you use spikes and you use temporal signals to essentially mimic more what the brain is looking like. Like you have synapses. In fact, like you have synapses basically send a signal in a temporal spike fashion. And it's Intel and others have some interesting work. I've collaborated with the Princeton group quite a bit. Paul Personnel on a several year long grant. Here's some work that we did in the spike neural network, and this particular work is actually just done on FPGA. There's nothing photonics here, but we can think about executing this now in optical domain with femtosecond lasers down the road. But before we go there, so the idea is, imagine you would like to know how symmetric is an image. Actually, some IQ tests sometimes do this. Like we need to see how symmetric some structures or so is. And it's apparently a test of intelligence, some people say. We can debate maybe over some good wine, like why that may be. So if let's say you have an input, and let's say the input is these 4 dots here, and if you ask, well, how symmetric is this structure? Then, while you can see, I can fold it like this. I can fold it top down. I can fold it diagonally. So notice then, if you create a symmetry map, so this center point is very symmetric. So let's make it darker. Yeah? And the way you can get the symmetry in a spike neural network is basically simply by building, let's say, a 2-layer neural network, an upper layer and lower layer. And the lower layer only fires if it gets a signal from the upper layer at the same time. Time of flight is basically distance. So this C is the downstream. It only fires when it gets a signal in time correlated from A and B, which means C is performing coincidence detection just by it creating a spike. Now, how do we do this? You can build a histogram of distances, and there's a certain threshold up here that you can set, let's say, arbitrarily. And you notice this is, again, coded to these points. So the center point has a very high sort of autocorrelation, if you so will. Therefore, it has this high peak, and you send this threshold like this red dot, and therefore then you can say, oh, this has a very high symmetry. Now, what do you use this for? You can actually do this for fingerprinting. So if you have some sort of signature, you can get some sort of signature of some sort of object that you like to track. Of course, this is good old military, but you can also do this for something very other interesting things. Like this is data from the global satellite data, and you see there's let's say there's some sort of dwellings and buildings here, and here basically it's just forest and vegetation. And notice vegetation, obviously nature has, like a forest has no symmetry, but these buildings and streets and roads have symmetry. You see these colors, like the hotter it is, like a heat map. You see, like see the symmetry popping up. So you can use this basically to do some sort of automated mapping of remote areas for disaster relief things and so on. So there might be some interesting fun things you can do. So briefly mentioned yesterday about the way we can we explore learning. So a bee, bee gets born, bee flies. It's really fantastic. But a bee cannot not fly. The bee cannot not select pollen. As a human, you get trained. You don't even know how to walk yet, right? For longest time, not to let alone fly and speak and do other great things in science and so on. But you have this trainable ability. All these neurons are ready by the time you get born, but they're not connected yet. So in the first couple of months, they basically or 24 months, they form. They create a dense interconnect. But notice actually, if you look here after 2 years, notice they're all equally, shall we say, at first order equally connected. And then once you start learning how to really walk and how to speak and talk and doing math later and whatever, you basically have certain parts really strengthened and certain weakened. This is known as Hebbian learning, like what fires together, wires together. And we were thinking about, well, can we build devices, optical devices in circuits that mimic this behavior? And this is sort of this work I briefly mentioned yesterday, but maybe too short. If you look at it, actually a synapses, there are certain functions that have basically been executed. So you have a calcium, you have a signal coming in, so calcium coming down the channel. If you have this calcium concentration can be mapped, in our case, it's simply a signal. It's how much light comes into such a device. They create now photogenerated carriers. The next thing is then these calcium-2 release this neurotransmitter. That release of neurotransmitter is essentially like the sort of generated biased current that drives then an electrooptic modulator downstream, and then it's like this neurotransmitter basically flies like across this gap, and then the other side is needs to be detected at these Ampa receptors. So these receptors now you can think about it, how receptive they are depends, well, how good this transmission across the synapse node is. In other words, is it a node that actually easily transmits or very hardly transmits? So you can set this how good receptive they are by simply biasing this modulator with a gate. You can put it in a preset state, more lossy or less lossy state. So the gate essentially.
You can mute or unmute yourself by pressing *6.
Thank you. So we can.
The host would like you to unmute your microphone. You can press *6 to unmute.
Okay.
The host would like you to unmute your microphone.
Unmute.
You can press *6 to unmute.
Okay. Glad you told us. Good. And then there's something called an ion pump. The ion pump basically it's basically like a reset of the whole cell. And we can do this by essentially applying a strong voltage on this gate and flushing out these charges that's sitting on this like floating gate. The last thing is we have this floating gate packaged between two oxides, which essentially allows it to have the states sit there. And as long as you don't do anything to them, they are basically held there. It's like a flash memory. This, of course, relates to memristive behavior.
They cannot hear you over the Zoom.
Oh, they cannot? Should I unmute myself over here?
No, not there, but
No.
like you need to unmute that one.
Is it okay now? Test, 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 online? We can monitor the chat maybe.
The host would like you to unmute your microphone.
No, it's still
You can press
mute
*6
for some reason.
to unmute.
Okay.
Press *6.
He has the mute symbol on his screen.
Yeah, it's fine now.
Yeah, I think it should be okay. Yeah, like you're right, Jordan. I have it actually right now muted here, but we have some microphones in the room that should work. Can you give a thumbs up that it actually works now? Okay, thanks, Blake. Appreciate it. Awesome. Yay. We prevail. Cool. Okay, very good. So this device has an interesting performance right now. It's like self-learning, self-adaptive. Like, how is it self-adaptive? So signal comes in, like again in this sort of neural-based system. Like signals. Trying to switch. Guess it doesn't switch. Let's see how we're stuck now. Here we go. Like signals come in, let's say from the top right, and basically flow to the lower left. Yeah. So as this case optical signal comes in, it basically presets the weights of this. And again, you have the opportunity to pre-dial it, to be a sensitive synapse, or blocking synapses. It's very small, it's pretty efficient, and it can be also pretty fast on signals. So yeah, this is, I think, an interesting direction that we are taking on to see what we can do for that. Next one is, I briefly mentioned now, so spiking neural networks. So essentially, in a perceptron, we need to weight signals, we need to sum signals, and we need to provide nonlinear activation function. And this is we're doing all like electro-optically. So we do an OEO. This is how the chip looks like actually, and I just highlighted. You see here in black, this sort of dashed line right here. This is actually the weight banks. In this case, this is like a 4x4 or like weight banks. The device in this particular case are actually simply electrothermal like modulators. It's kind of slow, but for training, it's at first order okay. It's a first attempt. We can do it faster later. The drive modulators that send a fast signal in are actually these two. Again, if you look at these two, these are actually typically MZI, so you see basically how huge they are, right? But again, they give us like 40 gigahertz basically fast signals. And then we are again in the electrical domain. You see here 4 detectors, like this is for 4 neurons. They basically perform the summation. Then you're in the electrical domain, and then you use this as a gate on these EO modulators to provide nonlinear activation function for downstream. So this is kind of an interesting direction. Architecturally, in case you're interested in this, so this is now, all what I've shown, this whole left, like previous slide, is basically one node. It's just one of these little bubbles. If you want to make a single layer now, what you do is, this is very elegant in optics now, you can have one of these nodes, And you see each of these modulators now is driven by a separate laser. Yeah? Let's say this is a yellow laser, and then there's a green and so on, blue laser, and then here's a pink laser. And they all get muxed together on one bus. So they all share the same signal, and they see all the weights from all the other neurons. So it's an all-to-all connectivity. Now what you can do is you can certainly build interesting, like let's say for recurrent neural network, an RNN, what you do is you have, this is the topology graphically, you simply have all these different nodes, and you simply have a single waveguide where you have this WDM signal simply broadcasted and feedback to itself. And this is essentially like a neural network memory type, an RNN. That's very common use. You see it actually here in this particular layer right there. The other option that you can do is you can actually build deep neural networks, like basically shown on the left here. So how do we do this? We use one of these broadcast and loop and weight rings, and these basically have color-coded, because this is all spectrally multiplexed, basically have individual weighting devices between the left and the next, the upstream and/or downstream broadcast and weight loops. So you simply have, again, another tunable ring filter, for example, here. And you can use 100 wavelengths these days, so to basically like have a 100 way of like multiplexing. In terms of energy per bit and speed, this is a bit of the holy grail map. So when when Intel scales basically the processors, essentially you're really moving up in this graph to this point. So you can actually overlay this data very well of an i7, i9, and so on. And it really approaches this digital efficiency wall in any processor. Turns out that these spiking-based systems, I mentioned like just before, even in electronics, are orders of magnitude more efficient than what we can do currently like in digital electronics. But we are still limited in terms of RC delay, in terms of speed. So we can speed things up by essentially going to the right now and basically bringing in WDM, parallelization, tens of gigabits per second rates. This particular program we were performing on this SRC Ncore and E2CDA had a goal of hitting 10 to the 18 multiply accumulate per joule. If you break down this number, you find a nice equation down here where it's actually pretty simple to understand. So there's some sort of quantum efficiencies, let's say laser efficiency, waveguides, and so on. Let's just say this is 5%, okay? Then you have, from a neuron's perspective, you get signals in, fan in, and you send signals out, fan out. In an all-to-all neural network, you have basically, this ratio is exactly 1, yeah? So that's simply a number. Then you have some constants, and then you can ask, well, how much charge do you need to drive the next stage of this network? It's a deep neural network. You have cascadability. You need to ask how many charge to get a decent signal to noise ratio do you need, and you can simply solve for how much voltage, how much charge you need, and then you end up, if you want to hit 10 to the 18, you can only have 60 attocoulombs. That's 10 attocoulombs. That's 60 electrons. That's it. Then you can ask, okay, so where are we with silicon photonics right now that you can tape out? Turns out you're burning about 10 to the 5 charges per modulator. So that's not good enough. And then here are some devices from our work where we said, okay, now we can actually approach this limit a little better. We're still not at this level yet. We didn't reach it, to be honest, but we're roughly away by a factor of roughly what's basically like 10x, like 350 electrons. So you see how sort of device technology can really influence system technology. We also looked into some nonlinear activation functions. So there's something called ReLU, rectifying linear unit. You probably heard about it. It's like basically the function is essentially flat and then stepwise linear. The issue is you don't like the stepwise linearity because you cannot differentiate it. In gradient descent algorithm, you're walking down this path and you cannot differentiate it at this point. So you need to kind of round it out a bit more. So that's something called a soft plus ReLU. And we engineered this by basically combining the Pauli blocking behavior of an graphene-based modulator with a free carrier linear kind of modulator to engineer the step-like function. You see the result over here. So here's a device, was published last year. We also then put this into a neural network. So here are these graphene modulators now in a larger neural network. You see the transfer function. You see a short device, a long device. You see some. We trained it down. We trained a neural network with I think this is 2 layers, each 100 neurons, and then we see how the network actually starts to classify, in this case, handwritten digits. This is simply MNIST. This was an older work from before. Okay. I thought in the few minutes that we have, then here, I just give you, and then this goes now into a big chip as well, where we actually put everything together, the weighting, the detectors, and then again the nonlinear activation function. This will be the first time that we actually do, or we actually show an all-optical, an electro-optical a nonlinear activation function on the chip, all integrated, which I think is an interesting direction. Little show and tell. This is like an automated probe station we have. Of course, we can build now an individual system with FPGAs. This is how like some of these earlier packaging look like. This is the fiber array coupler coming down, and then of course you have this is our tensor core. I thought I brought a little video to kind of if this works. Oh, here we go. Yeah. So we have this automated robotic load lock, because you see it's so dense with all the probes and everything. It's kind of very dense. So we have an automatic system. This is like some DC probes. This is the optical wedge. You see actually here the tensor core process like in detail. The system all operates basically by itself. You need to pre-align it, and then the system can probe the pads, knows where you are on the chip. We of course have bird scopes for high-speed measurements, with error rate testing, and all the other good stuff. Yeah, this is like this particular system has a certain speed limitation up to 12.5 gigabits per second, but you can always rent some that goes to higher speeds. Our network analyzer is up to up to 60 G. I briefly mentioned yesterday this laser integration, which the idea is you want to have the idea is to really build a photonic black box where you have an IC and the board designer does not know whether you have an electrical IC or a photonic IC. And it's really exciting because you can really now package systems at a much more higher level and use this technology called photonic wire bonding. So you have a laser here and you crystallize the little wire like this that you can basically can see here. And I thought the lasers we use are actually from HHI. They're from the Fraunhofer Institute right now. This is a 1x4 WDM wavebank. And what I thought was exciting to show here on the right is that the actual chips that were currently produced right now at Ames. And if you see, so we have now these modulators here, right? And you notice this is one modulator. You see here this and this is basically like a 3x3 tensor core processor. You see the detectors over here, but you see how huge the modulators are, yeah? Like these MZIs. So if we can actually have a very fast laser on the chip, we can directly modulate the laser directly. So essentially these guys go away. You save a lot of space, probably up to 50% of this of the chip. So a laser we recently built, I want to introduce briefly maybe here. I didn't I kind of skipped it yesterday. It's actually like a vertical cavity surface emitting laser, VCSEL. The state of the art right now is up to 20 G. The issue is at 20 G you get like nonlinearities, like something called gain relaxation oscillation. So the idea is you solve them or you overcome them by essentially creating multiple little cavities that basically feed the light together in a coherent fashion. And the device is basically showing here. So if you look at this, I don't know, maybe it might be too small, but you remember from physics, from the laser equations, you have dN over dt, the change of the carrier concentration with time. You have ds over dt, numbers of photons per time. And in this case, you added a third one. You see a d phi, a phase over time. So you can use these feedback mechanisms now to change the feedback based that you have from each of these cavities. And this is exciting because we made a non-transfer coupled the conventional, this black curve. You see, actually in terms of speed, we can go roughly a factor of 5 faster. This particular device is at 45 gigahertz, but this concept can be extended to roughly about 100 gigahertz as well. And of course, because you drive it harder now, you have these nonlinearities basically suppressed. You can actually get more light out, and the side wall suppression is actually 50 dB. So that's actually pretty nice. So you have a very clean laser essentially. Yeah, here's some more details about this. We drove it at 100 gigabits per second, so 50 gigahertz basically. And again, you can engineer this feedback here very nicely, carefully using this like Swede equation. This is all done in 3.5. We're currently working with NVIDIA and sort of building like larger systems. But again, we could take this now and put this as a next step onto these chips, and this will be very nice, like a very nice approach. Okay, I think we're getting a little short on time. Maybe just as a final note, let me talk briefly about this last topic. Then, I think it's very exciting to ask what are the fundamental limits about or the role of hardware. We talked about this a little bit. You have maybe applications, algorithms, and then hardware has a certain function. And I think the way to think about this is you really essentially want to reduce the entropy of a certain given problem with the least amount of steps. So if you take a certain problem complexity, so this is known as, let's say you can have polynomial complexities, non-polynomial complexities, or exponentially hard ones. So you have a certain system that has a certain complexity to reduce. And at a certain point, you say, okay, if beyond a certain entropy, I call it, yes, I have a solution. And the way you can think about it now from conceptually, so your problem has a certain entropy size, given by the problem, and your compute system has a certain entropy available. If now the problem entropy is larger than that of the computer, then you need to have n steps or some steps. And again, the way you reduce this entropy, the step reduction or the reduction per step is given by how hard your problem is. And it's interesting in this space, you can actually start sort of like do a bit of like a bit of bean counting. You can say, okay, so if I have one Neumann computer based on switches, every transistor gives you 2 states, 2 plus 2 plus 2. You have n transistors, you have 2 n states, physical states. In let's say a neural network where you have, let's say, in all-to-all connections, every neuron fans out to n other connections. Let's say you have n for one neuron, so you have n of those, you have n square. But of course, if you add entanglement now, meaning phase correlations between them, you basically have 2 to the n to the nth power. So you plot basically like the sort of compute potential, like basically this number versus simply available states. Well, one Neumann computer is linear in this, and then of course you have this really like dramatically scaling for quantum systems. So there's lots of potential, of course, that we can harness if we can create this entanglement. We wrote like a roadmap paper recently about it that sort of that talks a bit of the forward-looking view about what we can do in this entire space, in particularly integrated photonics. There's AIM photonics pushed out in the 5.0 PDK right now in quantum sort of modules, which I think very interesting, and that's something we can harness. So yeah, we looked into some tunnel junction-based devices that basically create photons. This is actually can this be played? I guess not. There was supposed to be a video here of basically some blinking light where we made some sort of tunnel junction-based device that essentially like emit a photon. So the thought was basically can we use the Schottky barrier effect? Can we use the Coulomb blockade effect to create very, very small tunnel junctions where we have like these negative resistances, where we essentially create a single electron tunneling regime to release an individual photon. If that could be done probabilistic, we would have like a deterministic quantum source. And this is all at room temperature. Can be done at room temperature if you look through the math. If it cannot be done probabilistic, we could use it, sell it as a random number generator. So either way, it's useful. Good. And then just very finally, we started looking into in this paper with UCLA together into some chiral systems. This is a graph, actually I made myself. Finally, some contribution to a paper actually. No, just kidding. So you can think about like if the probe is, so you have a probe and you have some matter. So light or a system interacts with some matter. So it can be basically non-chiral, the probe can be non-chiral, or matter can be non-chiral. So you're in classical, let's say, spintronics. Now you can make it matter chiral, and the probe still classical, or you can do the inverse. Chiral probe, let's say an OAM beam, for example, optical angular momentum beam, but you have regular matter, or you have some sort of, I call it probe matter enhanced system, where you have basically a chiral matter and a chiral probe, and they interact very nicely, and you have a nice bit of like spin transduction. That can be done all in a kind of incoherent way, where you just don't care what happens to the signal downstream. Or you can actually come with a coherent beam, where you either do space delocalization, or you preserve the phase in a basic quantum-based system. So I'll show a few examples to simplify here. So I think there's a lot of things we can do to really explore this chiral world. And we have been actually working on this a little bit. We built these angular optical momentum-based systems where we multiplex beams, and we now and we show we can drive it at a very high speed. And as next step, we're now exploring how can we. Here's a little video about the system. And we can also exploring basically how we can use this now to do this light matter transductions and where we preserve the spin. But this is a sort of T-shaped system where we basically multiplex 2 beams, like 2 OAM beams on a single carrier, and you can send it off through some turbulent media, and then you can basically take it back. Direction, I think where we do want to take it from here are doing this chiral induced spin selectivity, which basically is a fancy way of saying you can send a spin in, it can basically the spin can propagate, you can preserve a spin in, let's say, some sort of like material. And if you can do this, you could maybe build some sort of like more higher level system, like an Ising machine or so in the optical matter domain. Okay, so yeah, summary. Lots of all this work needs a lot of like clean room use for sure. I think that devices, it would be great to really get to like 100 plus G per channel on a baud rate for 6G ready systems, maybe 7G even down the road. I skipped the photonic sim. We can briefly talk about this offline. Talk about some self-learning devices and systems, and then talk about some inference-based system to possibly design systems which are more smart. So yeah, so big picture, long-term vision is really like to build more supercomputer like smartphones. We have some other thrust about go from perception basically to cognition and maybe to emergence even. And we have a pretty large program with some sponsors from the intelligence agencies around cryptographic processing. The ultimate goal would be to homomorphic encryption, which is actually a pretty fun one. So homomorphic encryption basically is you want to process data which actually happens to be encrypted. So it's basically like you want to process data off your bank, but you don't want to look at it. So it's in 10 to the 9 overhead. There was an IARPA program, Hector program that basically reduces from 10 to the 9 to 10 to the 6 overhead. And we believe with hardware, we can now maybe bring it down to 10 to the 3 overhead. So there's some interesting directions to take this. Okay, well, thank you very much. And yeah, looking forward to the fireside chat.
Yeah, okay. Thank you very much. That was a wonderful talk.
Thank you.
I'd like to say, if anybody has any questions here in the audience, on Zoom or in person, please feel free to ask them at any time. This is just a casual chat, just to learn more about Volker, his career path, where he's going, all that kind of stuff. So here we go. I'd like to say, yeah, I learned a lot from that chat, specifically about power dissipation, where we're going, because I think a lot of the problems nowadays are not just computing things quickly, but also doing so at low power. I want to say the Google quantum supremacy experiment was able to do things at such a low power compared to the supercomputers that could eventually simulate the same thing, right?
Yeah.
So I guess beyond speed and all that kind of stuff, what are the upper limits, do you think, for power dissipation in photonics for these sort of computational models?
Yeah, power dissipation. Okay, so yeah, so power dissipation, of course, in the end goes back to Joule heating question, right? So you need to see, essentially the key point is actually for optoelectronic devices is to bring resistance down. Essentially, some of the secret sauce around that is around annealing. So some of these high-speed devices, we developed basically in something that is, basically a patented like process where you actually anneal a certain annealing procedure to really bring the resistance down. There is, however, a catch, in particular with ITO. There's a catch where you need to be careful that if you bring it down, then you make the material more, let's say, shall we say, metallic. And in that case, then your extinction ratio on the switch may be reduced. So sometimes there are some trade-offs, but they can be studied, analyzed, and as an engineering optimized.
Yeah. What attracted you to this particular field?
The field of overall this
photonics, specifically understanding these power dissipation ideas. Why in particular did you want to study this instead of improving spectrum or something like that?
Yeah, well, I think I was always very interested fundamentally on understanding the fundamental limits of things. My background was actually in physics. I switched to engineering later on in doing my PhD, and in a way I think it's fun to ask some sort of fundamental boundaries. In fact, in engineering, they do it in a way too. We do it there too, where we basically ask, well, what's the fundamental limit of a certain, maybe even process or a certain concept? Now, how close to that can we actually get in a real device or a real system? Well, that's then. So I think you see, I think NSF talks about like there's fundamental science and then applied science. But in engineering, we never talk about this, and I would like to maybe propose this for us, like as a community. Like, why don't we talk about fundamental engineering and maybe engineering? And I think, in particular in academic setting, I believe it's a nice entity where we can really talk about the fundamental engineering side, where we just show the first concept, the first boundaries, and then we maybe theoretically give a forecast how far can we scale this, and then we can throw $100 billion at it and actually make it, right, and get the last mile basically.
Yeah, we're seeing that a lot in quantum computing. How far can we push these various platforms? Photonics, superconducting, all of that, right? Starting with the fundamentals, seeing if we can even get a topologically protected or even error-corrected qubit is a whole issue in and of itself, even if it's theoretically possible, right?
And that's an interesting point because, like even yesterday, let's say if you, like for instance, think about these Fourier-based optical processors. I mean, they were basically known since Joe Goodman wrote his book in the 1960s, 70s. So they're like around for a long time. And I used to have a slide. I call it I literally used the word the cover from Back to the Future, like the movie in the 80s. Or Back in Time, right? Like Back to the Future, because people were asking, well, we tried this in the 80s. Why now? What's different? To tell me, right? And I basically had two answers for this. The first answer is these optical systems, they literally can process at tera, even peta operations per second. Well, which also means you need to fuel them with that data rate. The reason we use these high-end FPGAs is, well, because they can give, actually the highest FPGA you can buy on the market right now is a virtual ultra-scale plus that gives you about 8 terabits per second sort of front-end bus, yeah? At a certain bit rate, of course. And well, guess what? We didn't have it in the 80s. So there was no way to even test the system, to stress the system. First answer. Second answer is there was no need. Digital electronics was quite good enough. I mean, what did you do in the 80s? You sent maybe not even an email, right? It's maybe text message. So the data rate that was demanded is like, meaning it's an ecosystem, right? I mean, now we have, 4K streaming. Well, that's a high data rate, right? So I think these, and of course now there's more AI coming to the edge, of course. We were driving this, in the car the other day, and then it's actually literally a fun fact. The first time I ever used really Siri, I was like, I have time on board, so I just said, hey Siri, and then she started responding. We had some interesting conversation there. But that all takes like processing. Now, of course, we can discuss how much of this processing takes on the device versus in the data center. But the push from the industry is to put this more onto the edge, in particular from DoD, because you can imagine if you send a signal across a channel, an RF, people can, you can tap into it, you can capture it, right? So processing locally will be moving forward, a much more interesting point. And my forecast is this phone that you have on your lap here, we will not have phones in 10 years anymore. Absolutely no phones. This thing will be like, oh my, remember the times we actually used to have phones? So what you basically will have some sort of thing in your ears, which you already have, right? Some sort of whatever, not to make commercially, but like these, all these Samsungs and like an Apples. And you basically interact more verbally with your systems. The system augments, the system forecasts what you want to be needing next, and it basically offers it to you, and you simply say yes, no, or you maybe tap something or so. Yeah. So haptics will become like a much bigger thing, like moving forward. And I really think these photonic technologies that we're building, these electronic photonic technologies, I should really say, basically have a good way to really push this frontier. So lots of fun.
For neuromorphic computing, do you need that high bandwidth in order to be able to process things from the brain specifically? Because now it seems like that might be one of the best applications for it. If things are happening so quickly in the brain, do you need these advanced technologies, specifically with power dissipation, right? And then also, being able to go at much higher rates, is that a necessary component to actually achieve Elon Musk's dream of having a computer hooked up to our brains, right?
To be honest, I still don't understand enough about, let's say, brainwave analysis. But let's say for this specific example, we need pattern matchers that probably use very little signals, because the brainwaves have a very small electromagnetic signals. So SNR, signal to noise ratio, will be a challenge. We may need to have some sort of gain or so. But yes, we have these electrodes hook up, and I think we've seen those where you can actually drive like a car. You can, if you focus very well, you can have this toyish. You sit in the car and you actually drive yourself forward by thinking. Have you seen those on the videos?
No, I haven't.
So these things do exist. Of course, they are very early stage, but we're kind of going more in this direction now. In general, I would say in AI, it doesn't have to be very, very, very the throughput. Meaning, so we have throughput, latency, and power, right? So in compute systems. So the latency really depends on the applications. Let's say if you really want to track a very fast-moving object, then latency needs to be small. Elsewise, latency is not such an issue. Throughput is a big question, particularly for learning. In learning, we need to have vast amounts of data, because just very simple. Let's say the tiniest data set is MNIST, which has 28 by 28 pixels, which is 784 pixels that you need to process, each at, let's say, 8-bit. You need to send them through multiple stages, through, let's say, neural networks. So it's a really you have millions, and then the data set has 65,000 images. So I mean, you have millions of tens of millions of nodes of individual multiply and accumulate. So yes, being efficient is extremely important fundamentally, but and certainly depending on where you are, you need to. I think we're still a few orders of magnitude away where we can be. Of course, the gorilla in the room is always like basically classification, inference on the edge versus training, right? So I mentioned yesterday the majority right now is still training, and anything we do maybe for fun at the edge is, you know, it's a small thing from the big pipe, but I think it's a good start, and I think it's important for us as a photonic community to start something where we really can show something that's very meaningful. They can really accelerate something. For instance, pattern matcher or an autocorrelator in the RF domain is worth, well, to quote the DARPA Max program, which is right now open, literally tens of millions of dollars, right? Just even at the developing stage. So I think photonics and optics can. I think my advice would be let us pick the applications a little bit, smartly. At least at this very stage. Now, if in 10 years we have proven a lot of these technologies and there are a lot of implementation. I mean, Aerospace Corporation. I guess I can disclose it, but Aerospace Corporation asked us to to discuss now putting some of these photonic tensor core processors on the CubeSats, so like Cube satellites.
Okay.
So very small, like like a box basically. So because they're very lightweight and have a decent throughput. So I think if you can latch on some of these really edge applications right now, I think that will give us a nice stamp for photonics processing, and I would also make a distinction between computing and processing. So I think right now I would like to say let us do signal processing maybe at the edge. We take an RF signal. It comes in, it's in the analog domain, like no DAC needed, right? Like you just take it in, you have an LNA, like no-loss amplifier, you dump that signal directly on an EOM, on the modulator, and then you just go, right? So the DACs cost you 30% of the overall system power. So I think what we also maybe need a little more is a system view of the world. And maybe part of the reason why I really wanted to have this vertical sort of group like I'm running and really want to understand the system as well, because in the end it's a system decision that we need to make as well. But yeah.
Okay. Well, thank you. Yeah. Do we have any questions from the audience in particular? Let me check. None in the chat. Okay. Does anybody in person have any particular questions for Professor Sorger?
I might have a question about these neural networks. So one of the other things that your brain does really well is that neurons can move, basically, at least the way I would think about it, when we program neural networks, we have layers, right?
Yeah.
But a neuron kind of doesn't really care about these layers and could probably go from one layer to another, could skip layers and so on and so forth. And so it changes, especially as you learn and as you move, your neural network completely changes. Is there, and I don't know a whole lot about neural network as far as how we do it programming now, but is there a way to, instead of having a layer, you have one that talks about one was recursive, is there a way to change that from time to time and have that be also a tuning knob? Because you can tune the connections between neurons, but can you change the way the neural network is shaped?
Yeah.
Is that also something that has been looked at?
Yeah, it's called Augmenting Topologies. In fact, there was one slide I literally skipped. I'm happy to show it to you afterwards. So we're using NEAT, N-E-A-T. It's a neuro-evolution of augmenting topologies. So it's basically a way of saying you have a neural network layout. Let's say you have n nodes, or actually not n nodes. You can have some nodes. You can add nodes. You can take nodes away. You can add layers. You can take layers away. And the way the system, this code is basically set up, it's by itself optimizing itself. It's actually a reinforcement learning based approach, where we have a Minesweeper based two-dimensional grid world setup. And the goal of the agent is to basically run around and essentially trying to cover the most ground, because most ground basically, let's say, means finding food, and if you find food easily, then you survive, right? And then they have a certain lifetime, and after this they die, and then only those who cover the most ground survive and go to the next can procreate their genes to the next generation. And then you run this n generations long. And what you see and then on the right side, I can show like the slide. On the right side, then basically you see how the topology, meaning the neural network itself, shapes itself. The beginning is very simple. It's like two layers, simply all connected, very, very, very straightforward. And then you see, after 10 generations, we were I'm actually, if I may disclose this, I'm actually really fascinated by the question, can we design a conscious machine? At least it appears conscious. There is this debate between hard AI and weak AI or so, but let's say it's a system that I didn't hard program, it just evolved, it emerged. And the answer is we can actually sort of do that right now. This is, again, completely software, nothing hardware whatsoever, but like we're using these models, these systems now, and but reconfiguration can come in by, let's say, literally electro-optic switches. You can have let's say, you can go left or right, yeah, like a switch, like not as in signal, but as in going left or going right, like basically going right. So you can set up these systems. In fact, I do have we have a program that we literally what's called ROC, Reconfigurable Optical Computing, ROC. And it's essentially like an optical FPGA. So you imagine, so we have a grid basically. We did this in like silicon photonics, and you can program each of these nodes now, like with the phase change material. You can set a certain weight to it, and then you can send light in, and they're all coupled to each other. And then you can use it as let's say as an annealer. Yeah, they're all they find the ground state, and then basically then. In this case, it's not Ising states yet because it's not phase coupled, but it's just amplitude coupled right now. But yeah, you can. So the answer is you can absolutely change the, let's say, phase or amplitude of an optical system, meaning, and then you can route signals. You can build this, but that costs you a lot of overhead. Yeah. So it's physically doable. We can even do it in the tape out or even in the clean room, but it costs you a lot of overhead. The question is it worth it right now? The answer is kind of not. That's why we train them. Yeah, we train them in a GPU or a TPU. And then you get the weights, you upload them, and even what you can do I think what you're asking is also, you can do a NAS, Network Architectural Search, NAS, so which is basically a way what computer architects do. They essentially, in an almost brute force-ish way, explore a whole bunch of topologies. Like you just test it all and see which one performs best. These simulations take months, literally, on a high-end computer system, so they're very expensive, very costly, but they can be done. And I like this neat approach, this more neuro-evolutionary approach, where we basically can, as opposed to hard, just test all the options. We just let the fittest survive, basically, right? The fittest give their genes forward, and then we use those like topologies and implement them, maybe then in hardware in a second step. So it's a two-step approach: training, and making them fit, and then transferring them into hardware. Okay. You may want to look into the DARPA lifelong machine learning. BAA. It's a program that already stopped, but I think they had a second generation where, like you train, system becomes better, but then an event happens, and an event happens meaning the accuracy becomes very bad, and the system can never recover, meaning machines cannot sort of adapt, right? So you're adding for this adaptivity, but these systems now basically can reconfigure themselves to get back up to speed and even essentially recover from this dramatic change that happened in the environment. They use this for radar processing right now and so on.
Very interesting. I think similar ideas have been employed in FPGAs, right? Reconfiguring the different configurations within the FPGA to accomplish some particular task. It's really interesting, and there's a lot of literature on it. We are past time a little bit. I do want to ask you one final question. What advice do you have for the graduate students and postdocs that might be listening in?
I think it's
all.
Yeah. No. Right. I think it's important to be. Shall we say to be efficient in everything we do. I think it's good to have a bit of a plan. My advice would be make sure work-life balance works as well. Now, of course, PhD is a crunch time, right? So make sure you put the time in. On the other hand, I think if you can find your own personal way to maybe just like release stress, go running, go jogging, whatever it is, right? Or meditate, or I don't know. So I think also make sure like there's a bit of fun, meet with friends. It's a group up. We're social animals. I think of course COVID was a hard time for that. But other than this, my other advice would be I guess I'm citing Steve here, but stay hungry. I think this is yes, you're getting the highest degree in the world, but you want to get a PhD in life. So I think I wouldn't say getting a PhD is easier. It's a process for sure, but I think key is almost once you're done with that, keep learning, keep questioning, keep asking questions, be curious, stay curious. It's very important. Maybe that would be a final note.
Okay, thank you very much. Everybody, join me in thanking Professor Sorger.
Thank you.